Alright, here are the solutions to the review. At the end, the last two questions that I tackle are the donut problem, followed by the London Eye Ferris wheel problem from the first part of the final. Remember, we're going to reassess on that concept, so it would be a good idea to take a look at that. So all of these should be pretty straightforward. The number of radius lengths in the arc of the angle, that's the number of radians. And so when we're on a unit circle, since the radius is 1, the number of radius lengths is just saying the number of single units in the arc length. And so we end up getting the very nice interpretation that on the unit circle, the radian angle measure that we're given is exactly the measure of the length of the arc of that angle. And that's why it doesn't matter how large of a circle we're using. Radians always takes into account the size of the radius. So when we get a bigger circle, obviously we get a bigger radius, and that's why we can still interpret an angle of, say, pi over 6 radians to be the exact same proportion around the circle. These terms should be pretty straightforward. Remember, cosine of theta is the x-coordinate after rotating theta radians, and sine of theta is the y-coordinate, and tangent of theta is the ratio between the sine and the cosine of that angle. And the way that we want to interpret it is that it's the slope of the terminal side. That'll help you make sense of tangent. These should all be pretty straightforward as well. A couple things to point out. At 5 pi over 4, cosine and sine have the same value. Tangent of 17 pi over 2 is undefined. That's because 17 pi over 2 is in the same place as pi over 2, and so their tangent is undefined. And at negative pi, tangent has a value of 0, and it's nice to interpret it in terms of the slope of the terminal side. That'll allow you to see why the slope is 0. Here we have the Pythagorean identity, and that is that the cosine squared of theta plus the sine squared of theta is equal to 1 for any value of theta. And the reason that this is, to prove this, what we're going to realize is that for any angle, cosine and sine are the x and y coordinate, where the terminal side of the angle intersects the unit circle. So what we can do is we can draw the following right triangle. So here's some angle theta, some random angle, and sine is the y-coordinate, and cosine is the x-coordinate of this point here. So we can create a right triangle where the side lengths are cosine of that angle theta, sine of that angle theta, and then the hypotenuse is 1. So we simply apply the Pythagorean theorem to this right triangle, and you get cosine squared theta plus sine squared theta equals 1, which is the Pythagorean identity. Again here, nothing overly complicated. F of x I think is a little bit easier to work with here. Remember, we're visualizing first, so we have a sine curve. We are noticing that there's going to be amplitude of 3, midline of -1, and you notice here that the value of b is 1/2, multiplying x by 1/2, and so that means that the period is going to extend, it's going to stretch out a little bit. And so if you're envisioning this, you know, sine starts at the midline and then increases and then hits its maximum and decreases. Anyways, we then go find the amplitude in the midline, 3 and y equals -1. That allows us to determine the max, which will be 2, and the minimum, which will be -4. The period is 2 pi divided by 1/2. 2 divided by 1/2 is 4, so you have 4 pi. And there is no phase shift. So then we can plot the first point, which is nice because there's no phase shift. Sine is going to have a y-intercept on its midline. There we have it. And then the next easiest thing to do is notice that since the period is 4 pi, the third midline intersection is going to occur 4 pi units to the right. And then halfway in between that, it's going to intersect the midline again, so that's at 2 pi. And then halfway in between these first two, there's going to be a maximum because sine starts increasing, and then there's going to be a minimum, and from there on out, we can sketch the curve pretty easily. For g of x, I'm going to just visualize first. We have a cosine function that is reflected. So cosine, remember, usually has a y-intercept at its maximum and starts to decrease. Because we're reflecting, we're going to have a y-intercept at the minimum and start to increase. So that's important. We'll notice there's a phase shift. We're going to have some sort of period that's different from 2 pi. Midline is 2, and the amplitude is 2. So midline of 2, amplitude of 2, that means our maximum is at 4, our minimum is at 0. The period is 2 pi divided by pi over 8, which is 16. And then we're going to have a phase shift of 2 units to the right. So I can plot my initial point, and the way I can do that is cosine usually has an initial value, a y-intercept, at the maximum. But it's been reflected, so it's going to be at the minimum. And it's phase shifted 2 units to the right, so that point at the minimum is going to move 2 units to the right, and that allows me to plot my first point. The period is 16, so it's going to have a minimum of 16 units to the right of 2, which is 18. And another 16 units to the right, 18 plus 16 is 34. I may have marked that a little bit too far to the right, but the intention was for this to be 34. And then you notice that cosine is usually a function which starts to decrease. But we have a reflection here, so it's going to begin by increasing. Another way to see that is in between 2 minimums, we're going to have a maximum. So a maximum is going to occur here, another maximum is going to occur here, and then I can just go ahead and plot my curve. All right, here we are applying the Pythagorean identity. We're told that the value of x is between 3 pi over 2 and 2 pi, which is in the fourth quadrant. In the fourth quadrant, cosine is of course positive, and sine is going to be negative. Finding sine of x, we can use the Pythagorean identity. Sine squared of x is 1 minus cosine squared. Cosine squared is 1 squared, 1, over 6 squared, which is 36. 1 minus 1/36 is 35 over 36. And then I need to square root both sides. So the operation that gets me from this equation to this equation is square rooting both sides. Now, when I square root both sides, I'm going to have square root of 35, as I have here, and then the square root of 36, which is 6. And I got to be careful. The Pythagorean identity does not determine the sign. I have to use the quadrant that I'm in to determine that. And since we're in the fourth quadrant, sign is negative. So this is going to be negative square root of 35 over 6, which is approximately negative 0.986. Finding the tangent, I'm going to take the sine, divide by the cosine, which is multiplying by the reciprocal of cosine. And that works nicely. I can use the exact value here because 6 over 6 is 1. So I have negative square root of 35, which is negative 5.916. And that should make sense because if I think about it, since the sine is very close to negative 1 and the cosine is actually very small, this is going to be a very steep slope here. And so I expect a pretty steep negative slope. That'll help me approximate the value of x, the angle. Since sine is very close to negative 1 and cosine is very close to 0, I would approximate x to be slightly greater than 3 pi over 2, since we're in the fourth quadrant and sine of x is very close to negative 1. All right, I want to create a sine and cosine function that corresponds to this graph below. Let's just take a look at the graph quickly. We'll notice a couple of things. The first is that the midline is at negative 1 and the amplitude is 2. So we can see here that the y-intercept is actually at the midline and then begins to increase. So this could be very easily made into a sine function. So we're going to go with a sine function first because there's no phase shift needed. So we'll start with a sine function. The midline we said was negative 1, so k is negative 1. The amplitude is 2, and so a we're going to say is 2. It doesn't look like we need a negative 2 since there's no reflection here. So we'll have 2 sine, and then negative 1 is the k value. What about the period? Well, let's look at the distance between two maximums. We can see here that this point is pi over 4 past 0, and this point here is pi over 4 past pi. So this distance is pi. Another way to see it is that the distance between the midline intersection here and the one that's 3 to the right is pi, or 2 to the right, I guess, is pi. And so that's another way to see the period, which is pi. Now, because the period is equal to pi, and we know that the period is 2 pi over b, we can solve for b. So pi is equal to 2 pi over b. 2 pi divided by what is pi? Well, 2. So b is 2, so I can now write my function y equals 2 sine of 2x, b value is 2, minus 1. Now, to turn this into a cosine function, I can do so easily because the sine of a value x is equal to cosine of x minus pi over 2. So I'm going to take my sine function, and I'm simply going to subtract pi over 2 from the argument. So I have sine of 2x, so it's going to be 2 cosine of 2x minus pi over 2 minus 1. Now you'll notice this looks a little different. Usually we have the b value factored out. We can do that. We could factor out a 2. And if you factor out a 2, you'll get x minus pi over 4. To see that this works, imagine we actually built the cosine function first. Notice that the maximum occurs pi over 4 units to the right of the y-axis. So we have a phase shift of pi over 4 units to the right, and that's exactly what this shows right here. Alright, so creating a Ferris wheel, I'm not going to create one for you. I want this to be something that you kind of do on your own here. But the thing that is most important is that you pick a period. In other words, how long you want it to take for your cart to go all the way around. And so I would pick something that makes sense. You know, think about being on a Ferris wheel, maybe 2 minutes or 5 minutes or whatever it is. And so that t is in seconds. So then you'll have to convert that to seconds. So if you want it to take 5 minutes to go around, 5 times 60, 300 seconds. And then you can compute the value of b much the way that we just did in the previous problem. And of course, draw your diagram of your Ferris wheel, determine how high above the ground you want it to be, how high up in the air you want it to go, and that will tell you, your midline and your amplitude, so on and so forth. Alright, so here's the donut problem. We have a donut, the interior is circular and the exterior is circular. The radius of the interior circle is 1 inch and the radius of the exterior circle is 4.2 inches. So of course the big hint here is that the interior circle is just a unit circle, and hopefully that will sort of clue you in to how you might attack this problem. But even if not, it should be pretty apparent if you simply follow the sort of instructions, if you will, of what Jason and Russell each do, and if you diagram the donut correctly, you should be able to tell pretty easily how you can compare how much of the donut each eats. So for Jason, I'm going to go ahead and diagram Jason here in green, and I will diagram Russell in light blue. So what Jason does is he measures around the inside of the donut here, and he measures 2.5 inches around the inside of the donut. So if the radius is 1 inch, I'm going to try and draw this to scale here. Let's say there's the center, and if this distance is 1 inch, then 2.5 inches might get him, I don't know, somewhere out here. Okay, so we'll say he travels like that, and that is 2.5 inches. All right, and then what he does is he extends a line from the center of the donut through his starting and ending points all the way to the exterior of the donut. So take that step by step. He extends lines from the center through his starting point to the exterior and through his ending point, which is right here, to the exterior. Just like that. Okay, then Russell, he does something very similar. He measures 10 inches from the point Q around the exterior, and if we know that the radius of the exterior circle is 4.2, so we know that this is 4.2, and I'll go ahead and label this. So the radius of the interior is 1, and the radius of the exterior, I'll mark that over here, is 4.2. That's a little light, but you see what I'm saying. So if this is 4.2 inches, then this might be another 4.2 inches, another 4.2 inches, I don't know, somewhere around here, it might be 10 inches. The point is I don't want to end up right in the exact same place because I want to be able to visualize the comparison between how much each eats. All right, and I'm just diagramming here. The diagram isn't going to tell me for sure which one eats more, but it's going to allow me to see how I can compare the two. So let's just say it ends up, I don't know, somewhere over here. So he travels around the exterior of the circle, he ends up there. So this distance that I'm outlining in light blue is 10 inches. Okay? And then he does the same thing. He extends a line from the center to his starting point and to his ending point on the exterior of the circle. Okay, now I went over that in purple because the light blue was a little hard to see. All right, and then each is going to eat the amount of donut that is between their starting point and ending point and along the arc. So let's just consider what that means for Jason. So this is the line at which he ends, and this is the line at which he begins, and the amount of donut that is along his arc is this donut here. For Russell, same idea. along his arc, which is right there, is this amount of donut there. So based on our diagram, it's pretty easy to tell that if this was the mathematically exact amount that each ate, that Russell would end up eating more of the donut. Now, how do we actually compare that? What causes Russell, according to our diagram, to eat more than Jason? Well, it's pretty obvious because he has created an angle that is a little bit bigger, right? Whereas, as we can see, Jason's angle a little bit smaller. This should remind you of how we actually measure an angle. An angle is measured by the number of radius lengths in the arc that it creates. So for example, the angle that Jason creates, the arc length is 2.5 and the radius of his circle is 1. So the angle that he creates is an angle of 2.5 radians. Now Russell, he creates an angle of, well, we need to do a little math here to figure this out. And here's why. His arc length for his angle is 10 inches. But this is around a circle of radius 4.2. So to compute the angle that he creates, we need to see how many radius lengths are 4.2 are in 10. In other words, how many radians is the angle that he created. So we'll say that Russell creates an angle of 10 divided by 4.2, because that will tell us how many times 4.2, the radius, goes into the arc length of 10. And once we compare the two angles that each creates, we can see that Jason is taking up more of the donut than Russell would be, and so he's going to eat more of the donut. This actually isn't the only way to do this problem. You could also think about how you're taking a circle of radius 1 and extending it out to become a circle of radius 4.2. And so what you could do is multiply the dimensions here by 4.2. So you would multiply the arc length by 4.2, and 2.5 times 4.2 is greater than 10. It's in fact 10.5, and so that would be the arc length that Jason creates if he were to extend it all the way out to the exterior of the circle. And so that's another way to compare the two of them. But what's cool about this problem is it allows us to see how radian angle measures do not depend on how big of a circle you use to create them, because it's all about how many radius lengths are in the arc length that you create. All right, we're going to take a look at the London Eye problem. Hopefully you have your exam in front of you and you've already redone it a couple of times. But if not, here are the questions. So the London Eye is basically a very big Ferris wheel, and we're told that it has a diameter of 120 meters, and that of course tells me that the radius is 60 meters. We're also told that it rises 135 meters in the air, and that one revolution takes about 30 minutes. So a couple more annotations that I can make. A key understanding is that the period is, of course, the time it takes to make one full revolution. So we know that the period is 30 minutes. And also, since the distance from the top to the ground is 135 meters and the diameter of the entire wheel is 120, that means that the gap between those two is the distance above the ground. So this distance above the ground is going to be 15. All right, we are also told that when the ride begins, so they load the passengers, and once the ride actually begins, you are at the very top. So your observation pod that you're in actually starts from the very top. So we can just mark that here to remind us where we begin. All right, so now we can dive into the problems. The first one says, if the ride turns an angle of 1.75 radians, what is the distance that your pod has traveled along the circular path on which it is traveling? So remember, a radian angle measure, and this is the key to the whole problem, a radian angle measure tells you the number of radius lengths on the arc that creates the angle. So if we are traveling 1.75 radians, then the arc that we are traveling along is 1.75 radius lengths, which means the arc is going to be 1.75 of these radius lengths of 60 meters. So we can simply do some multiplication. We are going to find 1.75 times 60, and that will tell us the distance of the arc, which is 105 meters. Alright, now I want to help you understand where this is coming from. So what's happening is that your ride is turning an angle of 1.75 radians. So we can just think about where your cart starts, and this being the initial side, and it's going to rotate, somewhere around here, and it's going to be an angle of 1.75 radians. So we can actually sort of draw that terminal side here, and I'm just making it an arbitrary size. And this angle is 1.75 radians. Now, what we know about radian angle measure is that this number here refers to the number of radius lengths in the arc that has created the angle, essentially. And so what we can do is find the distance, or the length of that arc, by taking the radius and multiplying it by the number of radians. So that gives us our answer here. I'm not going to write these out in full and complete sentences to save space, but you certainly should if you are practicing for an exam. Alright, next we're going to write a function that gives the height of your observation pod over time. So height we'll call h, and time we'll call t. And that means we're going to write a function h in terms of t. So h of t is what we're going to build. H of t. Now we got to decide what type of a function we're going to write. What do we know about the height of the observation pod over time? Well, it's going to decrease, it's going to reach a minimum, and then it's going to increase just the same way that it was decreasing back to the top and go on and on, so on and so forth. And so we want to use a periodic function, a trigonometric function. And now we just have to decide which parameters we need to set, and whether we're going to use a sine or a cosine function. So I'm going to go ahead and write the general form here, and that will allow us to get a good view of what we need to decide on. So we're going to have a, now it's going to either be a sine or a cosine function. The b parameter, and the input variable is t, so it'll be t minus h plus k. Now, I think it was video 6.10, maybe 6.09, where we discussed how we can systematically go through and determine the various parameters that we need and kind of the order that makes the most sense. So the two that are most kind of easy to find and that are linked together are the amplitude and the value of A and the midline. So remember, the amplitude is the distance between the midline and the maximum, or the midline and the minimum. So let's go ahead and just figure out what the maximum is going to be, what the minimum is going to be, and that will help us figure out the amplitude and the midline. So we know that the maximum height is going to be 135 meters. We were told that already. The minimum height is 15. Now the question is, what's the midline? This is actually pretty easy. You could add these together and divide by 2 to find the average, or the midpoint. But it's probably easier to just look at the visual we have here. If this is the minimum, halfway to the maximum is going to be a whole radius length, right? 60 meters. You can see that pretty clearly illustrated here. So 60 plus 15 is 75, and that tells you that the midline is y equals 75. Or rather, we should say probably not y, but h equals 75, right? Because we're using h to represent our output variable of height. So the midline is 75. That tells us that our k value is going to be 75. And this also tells us that the amplitude, I'm not sure why I wrote it backwards, but the amplitude is going to be 60. Because it takes 60 meters to go from the midline to the max, and 60 meters to go from the midline to the minimum. And you can notice the correlation here. The amplitude is going to be the radius. Alright, so let's go ahead and start writing our function here. Now, I know that A is going to have an absolute value of 60. I still might have to have a negative 60. We'll figure that out when we look at the cosine, sine, and the phase shift. So we'll go ahead and just put 60 for now, give ourselves some space to put a negative sign there. And we know that the k value is going to be 75, positive. All right, now let's go ahead and take a look at the value of b. Remember, b is related to the period. The period is 2 pi over b. So remember this, period equals 2 pi over the absolute value of b, and we can just make b positive. Okay, and the period we know is 30 minutes, so we have 30 is equal to 2 pi over b. All right, I need to solve for b here, so I'm going to multiply by b on both sides and divide by 30 on both sides. And that gives me the value of b will be equal to pi over 15. So something definitely less than 1. It's close to 1/5 there. So let's hold on to that. We're going to figure out the rest of the function and then incorporate the b value. Last thing we need to decide, are we going to use a sine or a cosine function? And depending on which one we use, do we need to incorporate a phase shift? So let's remember those key characteristics of sine and cosine. A sine function with no phase shift is going to have a y-intercept at the midline, meaning that when t is 0 here, we would have a height of 75. Is that where we're supposed to be starting though? Not quite. We're supposed to be starting at the maximum. And luckily, cosine without a phase shift has a y-intercept at its maximum, which is exactly what we want. So we can use a cosine function with no phase shift, and we don't need to reflect by making the a value negative, because we want to begin at the maximum value, and then from there we want to decrease. So we're going to go ahead and make this a cosine function. There is no phase shift, so h is 0. The b value is pi over 15 times t, close the parentheses there, and that is my function for the height. Alright, let's take a look at letter C now. How long will it take the observation pod to reach an altitude of 89 meters for the second time? Show the work that leads to your answer and explain your method. Okay, let's break this down here. First, what are we trying to figure out? We want to know how long it will take, so we're looking to solve for t. Okay, what do we know? Well, we know that we want it to reach an altitude or a height of 89 meters. I'll get to the for a second time here in a minute. Altitude of 89 meters, this tells us that our height, h of t, needs to be equal to 89. Okay, so just looking at what we've annotated here, we can really, if we've put together our function correctly, we have a really nice setup. We can set our function h of t equal to 89 and solve for t. Now, if you just take a look at what that will give us, we'll have 89 is equal to 60 times cosine pi over 15t plus 75. We actually we haven't learned about inverse trig functions yet, and so we're not going to be able to solve this by hand, but we know that we can solve an equation using a graphical method, and so we can either sketch the graph by hand and approximate the intersection, or we could use a calculator to find it exactly. So I'm going to show you sketching it by hand, and then I'll also show you the exact answer. But before we get to that, let's see how we can use the diagram that we have to come to a good approximation before we tackle the plan that we just laid forth. So I want to know how long it's going to take my pod, which starts at the top, to get an altitude of reach an altitude of 89 meters for the second time. So think about your trip. Here you are at the beginning. You start, you're going down. At some point on your way down, you're going to reach 89 meters. Maybe that's right here. So let's make a little note. Maybe that's 89 meters. Okay, that's the first time. Then you're going to keep going. You're going to reach your minimum. And then on your way back up, you're going to hit 89 meters above the ground once more. So this is what we're looking for, the time it takes to reach this point. So we can make a little approximation here. Think about it this way. It takes us 30 minutes to go all the way around. So it's going to take 15 minutes to reach the minimum. And then from there, it would take another 15 minutes to go all the way back to the top. So we can sort of break it up into intervals. We can say, okay, how long is it going to take us to go from the minimum back to the midline of 75? Well, you might say it'll take half of 15 minutes, or 7.5 minutes. So think about it this way. We've got 15, and then another 7.5. That's 22.5. And then you can say, okay, well, 89 is a little closer to 75 than it is to 135. So I might say it'll be a little closer to 22.5 than it would be to 30. And I might come up with an estimate of somewhere around, I don't know, 24 or something like that. So just by reasoning it out, I have a nice estimate of about 24 minutes. And now I can go into solving this graphically with a great approximation. So what I'm going to do is I'm going to go ahead and sketch the graph by hand, make my approximation that way, and then I'll show you how it would look if we used our calculator to solve. Alright, so here is the setup for my axes. The height is the y-axis and the time is the x-axis. The cool thing is that to sketch this by hand, I actually don't need to even have gotten the function correct. I can just use common sense from what I know at the beginning. So I'm going to graph the function h, the height of my pod, in green, and I know that it begins at a maximum value and that its period is 30 minutes. So let's say here is 30. It's going to reach the maximum again. That means halfway in between, let's say 15 minutes, mark that here, I'm going to reach the minimum, 15 feet. Oh, I should have made that green. There we go. So now I can go ahead and sketch my curve. So there's my function h. And I want to know where it's going to intersect the line y equals 89, or h equals 89. So I can go ahead and draw that out here. I'm going to make it dotted. And here is the intersection that I'm looking for. Alright, so I might say, okay, this is 15 right here. And this looks a little bit more than halfway between 15 and 30. Halfway would be 22.5. So again, as we talked about, I'm going to estimate that this is about 24. Okay? So using that, I can come up with a nice approximation. And now we can use our calculator to get the exact value. So what we're going to do is we're going to solve the equation h of t is equal to 89. So in my calculator, I'm going to graph h of t in y1. That's this right here, in y1. And then I'm going to graph 89 in y2 and find where they intersect. And doing so will tell me the t value that I'm looking for. So I put that into my calculator, I find the intersection, and I get approximately 23.624 minutes. Now, it's important that when you are looking at your calculator, you find the intersection that occurs here, not here. This is, of course, the first time, right there, and this is the second time, the one that we're looking for, there. Alright, let's take a look at D now. What is the speed, and I'm going to do this problem down here below. What is the speed at which the ride turns? Include appropriate units. Alright, so how do you measure the speed that something turns? Or another way of thinking about it is the rate at which the Ferris wheel is turning. Remember, a rate is the change in whatever you're measuring, so in this case, the change in how much it's turned, over some unit of time. So how do you measure how much something is turned? Well, you use the angle. And that's going to be the setup for our problem. We're going to want to know the angle at which it turns per some unit of time. Now, luckily, we are told this at the very beginning of the problem. We're told that one revolution takes about 30 minutes. So if we use this piece of information, one revolution, what kind of an angle is that? Well, one full turn is an angle of 2 pi radians. So our speed is equal to 2 pi radians. And how long does it take for it to turn 2 pi radians? It takes it 30 minutes. So we have 2 pi over 30, and we can approximate this to either pi over 15 or 0.209 radians per minute. And that should make sense because if you want to go all the way around, it's going to take you 30 minutes, and all the way around is 2 pi radians, which is about how many radians? 2 times 3 is 6, so a little more than 6 radians. And so every minute you're not going to want to turn very much because over 30 minutes you're going to need to get all the way up to about 6. And so 0.209 radians per minute should make a little bit of sense. Now, that is the answer to the last question there, and hopefully this was helpful. If you have any further questions or need some clarification, don't hesitate to shoot me an email or drop by my office.